Okay, so good evening everyone and welcome to week 13 of this course. So I don't know why people are sitting behind, so if you don't want to attend you can leave or you can come in the front. Anyway, so today we're gonna look at continue our discussion on reinforcement learning and look at some recent methods. So actually we're gonna revisit some of the topics that we discussed last time, so you kind of understand the formalism and the objects that are used to come up with a reinforcement learning solution. So before that, as usual, announcements. So as usual, please give feedback on the lecture after the class. So the form for today's lecture is there. One second. And the second point, which is very important, is course evaluations. I don't know, did you guys get an email from UIC? Yes. Okay. So it's kind of important to improve the overall program itself, as well as the course offerings. So it's kind of important that you give somewhat detailed feedback there. Exam grades, we have already checked few. I think 1/5 of the sheets we have checked. So it's not bad. So hopefully by next even Wednesday or Friday we should be able to get back with the numbers, and then you can check the scripts in my office after that if needed. Okay. So there were some questions about the project, so some details, some of which I've already discussed last time. So in terms of logistics, we need to upload the presentations on the course website. So I'll make a link available soon, so you can upload it there. If there is a demo component, I strongly suggest that you use some screencast or video recording to just show how your project works. And so as I said, there will be 7 minutes, and you kind of want to keep the presentation short. And refer to the project instructions, especially in terms of how you will be graded for the presentation as well as the overall project. Final report is due on April 28th, and small incentive for people to perform well. So top 6 groups, so top decided by me. I will get a bonus of 3% if they participate in a poster presentation for I think the CBA is organizing some student expo. So but I think on April 28th you already have several other engagements. Some what was that? I don't know. There are some other events as well. I think you guys are busy in the morning, but some expo is going to happen in the afternoon, and so this bullet point is towards that. So it's 3% on the overall grade. So it's not 3% of the 45% of your project grade. It's the overall plus 3. So it can change your grades, depends on where you are. Okay, so in terms of timeline, so today we're going to cover deep reinforcement learning towards the end. So it's going to kind of bring back the memories of the CNN that we learned in the first, second, third lecture, to see how it's actually used in building an AI agent. Last time we saw some demos of a self-driving car and so on. So these are some of the key tools to get to that stage. So okay, so today we're gonna start again with a review of basics of reinforcement learning. What are Markov decision processes? What was the state action value function? And one algorithm that we covered last time called Q-learning. And today we're gonna make the previous solution is enough if you have a really small toy problem, but you really want something else to scale it up to potentially a self-driving solution. So what does it mean to scale up? What does it mean to build an agent in a really complicated environment like the human world, right? So to do that you need some tricks, and one of the tricks is function approximation. And we'll just see that instantiated in a couple of agents. One is called DQN, the other one is called AlphaGo. So we'll see how they kind of use essentially Q-learning or some of the objects that we see like state action value function to do well in their respective domains. Okay, so let's review our reinforcement learning. So this was the slide I flashed last time, that this month's technology review magazine has rated reinforcement learning as one of the top 10 breakthroughs of this year, among a lot of other potentially very high risk but futuristic technologies, right? So what was the need for reinforcement learning? We looked at multi-arm bandit long time ago, two lectures ago. There we were only interested in we didn't know. So let's say we had 5 actions. We didn't know which action was leading us to high reward, and we wanted to figure out by trying actions in again and again and again to figure out which action led to the best reward and keep playing that for as much as possible. Then we introduce the notion of state or context, which would say, in this context, what action should I take? Which article should I show? Which ad should I show? How much should I refill my inventory? Or which turn should I make in self-driving? So given the state, you would pick action. So this vastly increases the complexity of the problem. So, but the interesting thing was the action that you take only influences the current reward that you get, and it doesn't influence what is the next context or state that you see. Okay, that was contextual bandits. And the fully general problem of sequential decision making was when your actions also influence the next context and the next state that you see. So if you take a left, with your self-driving car, then you may hit the pavement or something like that. So that's the next state, that's the next context. So in that context, you will again try to take an action which may be, different. So your future is influenced by the actions that you take. So that was the full reinforcement learning problem. And we saw some examples. Atari, I think it was Breakout, and we didn't see AlphaGo demo as such, but AlphaGo is another example of use of reinforcement learning techniques at scale. Of course, there are many other applications, and 3 lectures are not enough to cover the applications fully. So let's get back to kind of the key ingredients in reinforcement learning. So it's an instantiation, or it's a version of the problem of sequential decision making. So sequential decision making can come up in many varieties. Okay, so one variety is I don't know if you've gone through an algorithms class, you might have heard of dynamic programming. So there is a sequential nature to certain types of problems, like finding out the shortest path in a graph and so on. There's also sequential nature in, for example, operations management, where, for example, you're the inventory manager for a warehouse, and you kind of need to take decisions, and you have demands appearing in stages, right? Demands and supplies appearing in stages. So what are the key ingredients in this version of the sequential decision making problem? There's an environment, and there's an agent which takes actions in that environment. The actions influence the future, and the agent gets a feedback signal, and it can potentially be delayed. So what does it mean? In contextual bandits, you take an action, you get a reward in the same time step. In reinforcement learning, you take an action, you may never get a reward till for the next 100 steps, right? For example, in a game, let's say in AlphaGo is a part reinforcement learning agent. So it plays the game, but when it takes actions, it will only get to know whether it won the game after the game ends, and that is not certain, right? That's not going to be immediate. And the objective is going to be how to maximize total reward. So this feedback signal is, you can think of the feedback signal being high as a good reward, the feedback signal being low as bad reward, and so you want to maximize, the reward collected. So pictorially, this is what's happening. So there are at least these objects, right? So at time index, so let's think of discrete time. So at time index t, the agent knows which state it is in and what was the reward that it got, let's say, from before, or maybe there's no number there. So state is essentially a measurement that you make about the environment, right? So where am I in this room? So I'm in the 1,1 position in this grid or something like that, right? So I take an action AT, and as a response to that, environment gives me back the next state and a reward. Okay, that reward can be 0, which means it's probably not informative. So or it could be informative. 0 means maybe good reward compared to, let's say, minus infinity or something like that. So this is what happens in stages. So that's the sequential nature, and the decisions that you make are these A actions, right? Yeah.
So does the state and the reward depend upon the previous action? So ST plus 1 and RT plus 1 depend upon AT.
Yeah. So you respond with AT, In the next round, you get an ST and RT, right? So, yeah, so that's the difference with contextual bandit, right? So your actions influence what is the next state, yeah, and there could be so this reward may also depend on what you did here, and this reward may also depend on what you did here, okay. But we just don't show that dependence explicitly here. This reward can be dependent on this action because this reward happened because of this state and this action, and you reached this state because you were in this state and this action. So you can reason about why there's a long-term dependency. Okay, so that was the nature of an agent and an environment. Yeah.
In case of chess, would it be a reinforcement learning or a combination of conjugation with the chess state?
No, if you can describe the state, so CNNs come up when you need to handle images, right? So in a chess game, if you can tell me the positions of all the pawns, then you don't need a CNN as such. But we'll see why function approximation is used. So we'll get to a function approximation part of this lecture where we are going to talk about why we can use CNNs or something like that. Yeah. First of all, chess is also not stochastic, but and also chess involves two players. So as long as you make the second player part of the environment, then you should be fine. But we will see that you don't need to make the other player part of the environment.
I mean, when you're actually the reward is in a way what you're going to get when the other player gets an error.
Yeah, in chess, for example, you won't see all these. At the end of you will have a series of interactions, and maybe it ends in a checkmate or whatever, stalemate or something like that. Then that reward number can be +1, -1, or 0 in case of a draw, and that's the number that you see at the end. So throughout all the moves that you make, you don't see anything. So that's why you need to make a long-term planning. There's a trade-off with respect to time, and there's also trade-off with respect to exploration and exploitation, just like in contextual learning. So there's like two levels of trade-offs happening. So this will become more clear as we look at some of these agents. So before that, let's revisit what we saw last time. An RL agent typically will involve three, one of these three or some of these objects. So one of them is going to be policy, which is the agent's behavior function. So policy just means in this state take this action, just like in a contextual bandit in this context take this action, right? Value function. Now this you can also define value functions for contextual bandits and so on, but a value function is going to be how good is each state, or a state comma action pair. Okay, so it just tells you what is the value of being in the state, or what is the value of being in the state and taking this action. It's just a number. It's a score. For example, you having a very high grade in this course is a state, and you can attribute a high value to it potentially or low value to it. So that's just a score that you're assigning. Okay. And a model is going to be agent's representation of the environment. So it's a model of the environment basically, just like any model, right? So last time we saw we use the symbol pi of s to represent a deterministic policy, and pi of a given s to represent a stochastic policy. So a policy is just this, similar to contextual bandits. And for example, in this maze domain, which is described by, let's say, rewards of -1 per time step, actions being the 4 directions, and state being the agent's location, so x, y, two numbers. This could be an example policy. So it just says in this state take a best action or something like that. So these red arrows represent a policy. Okay. And then, so what's a value function? Value function is going to be a prediction of the future reward. How good is that state? So how do you quantify that? It's just the if I have fixed the policy, then it just tells me I follow that policy. I'm gonna keep collecting a bunch of rewards till something happens, like end of the game, or maybe it's a episodic Markov addition. Sorry, it's an episodic domain or something like that. So you just collect a bunch of rewards and the expected value over the dynamics of the environment, and in case your policy is random, so that's the number here. That's the score that you assign to a state. Okay, this is just called the state value function. There's another value function called the state action value function that we're going to see shortly. Okay, so for example, here the value of being in the state is -1 because because the reward at this state is -1 and the next reward is 0 because you reach the goal, so you terminate. So the sum of the rewards is just current reward plus the next reward, for example. So 0 plus -1 is -1. So it's just so this is just an example to show I can attach a bunch of numbers to each state. That's all. So we'll actually get to what the precise numbers should look like again in a few slides. Okay, so the third component is going to be a model. So model predicts what the environment will do next. It's the dynamics of the environment, right? So that has two objects or two functions. So the script P represents the transition probabilities, and script R represents the rewards that you can get. So these are functions of the current action, the current state. So reward is a function of current action, current state. So it can be random, in which case this represents the expected reward, and the script P represents the transition probabilities, which just say if you are in state S and take an action A, which next state would you land in. Okay, and these need not be probabilistic, so it can be it can be a degenerate distribution which just goes to a specific next state, right? If you take a sharp left on a straight road, then you're definitely going to hit the pavement or something like that. Okay. Yeah, so here just the grid layer represents the transition model and the numbers represent immediate rewards, and we just said that the immediate rewards are all -1, which are constants, which are not, again, not stochastic. Okay. So but then I just define these three quantities, but we again going to look at the same quantities through the framework of Markov decision processes, and last time through the framework of Markov decision processes, and then we'll address the question of optimizing for the best policy in realistic environments. Okay, so realistic environments will be the second part of this lecture, where we're going to look at deep questions of scalability using function approximation, and optimizing is what we saw last time, and to do so we kind of try to wrap our head around what is a Markov decision process. MDP is just a short form for Markov decision process, is a useful way to describe the RL problem, and it can be understood using the following sequence of progressions. So first we start with the Markov chain. Okay, a Markov chain, think of just finite states, let's say 5 states. Okay, it's just it can be described by transition probability matrix, right? So state transitions happen autonomously. There's nothing that you're affecting the Markov chain. So once you define a Markov chain, at every time and talk about the starting state, you can just generate a sequence of next states, right? That's what it is. It's autonomous. You can add rewards. Okay, so it becomes a Markov reward process. So for every state, you can attach a number, which is called a reward, and it becomes Markov reward process. Again, still autonomous. Now you can add actions that influence the state transitions. Then it becomes a Markov decision process. So once you exogenously talk about introducing an action, then a state and action will lead to a reward, which is a single number, and also the next state, S prime. So just to reiterate, the transition probability matrix or Markov chain or Markov process is just this: P subscript S to S prime is the transition. Okay, this we have seen multiple times. I think we saw this in the sampling methods for inference and graphical models, right? Next is Markov chain with rewards. All we're adding is a script R term, and you can ignore the discount. Discount is the same discount that we saw earlier, which was trying to define the value. Okay. Actually, you don't have to ignore it. Let's say there is a constant less than 1, which defines the Markov reward process. Okay. Then with that definition, we can now, for a Markov reward process, we can define the return, which is G subscript T, to be the total discounted reward from time step T. Okay. So this will be an important quantity, because with this we can define what a value function is. So we're calling rewards the instantaneous rewards, that these are called rewards. Okay, and GT we are calling it a return. Okay, it's just the sum of all the rewards that I can get for this Markov chain with rewards. Okay, because the Markov chain anyway proceeds autonomously, I can just collect these rewards, right? till maybe there's a terminating state in the Markov chain, or it keeps going on and on and on, and hopefully these numbers are finite and gamma is less than 1, so that this sum is constant, is bounded. Okay. Yeah.
What exactly is gamma? What does gamma represent?
You're discarding the future value of your rewards. Similar to in finance, you discount the future value of money.
And we need to recalculate and discount it.
Yeah, similar notion. Yeah. I mean, for purely technical reasons, it's just there to ensure that the sum is bounded. But you can think of it as discounting the future reward that you may get in this reward process. Maybe you care about the rewards, the numbers that you get early on. I mean, here we don't have any control anyway, so here it's just the numbers that we get. But we'll see that later on. You can think of it as a discounting. Okay, so given the return, the state value function Vs that we kind of introduced at the beginning as an important object for an RL agent is just going to be the expected value of the return starting from the current state. That's it. So one of the three objects value function we just defined. Okay, and we don't have a policy yet. So we start from a Markov chain. We got a Markov reward process from which we can define just a value function. Okay, one of the objects of the RL agents. Now, the value function actually can be decomposed into two parts: an immediate reward and a discounted value of successive state. Why is that? You can just plug in the definition of GT. Okay, and you can do some manipulations. You can take gamma common, and then you can see that this is going to be GT plus 1. And you can, because of linearity of expectations, you can send some, you can take the expectation for the future dynamics in, and that will be the V term. Okay. So this slide is just trying to show that there is a recursive relation between the value of state S and the value of next state ST plus 1. Okay, ST plus 1 is going to be random potentially because of the dynamics of this environment, but there's a relation between two different states values, right? And the same thing is represented diagrammatically here. So the same equation represented here. So a circle represents a state, and there's number attached to the state. And from that state, I can probably go to a bunch of other states. Let's say in this case 2 states. Then maybe I can get a reward for going to S prime. And for S prime, there's a number associated which is V of S prime. Then these two numbers are related in this way. Okay. The sum is over all the next states, so in this case there could be 2 next states, right? Any questions so far? Okay. So now the systems, the Markov chain and the Markov reward process were autonomous. Now we're going to introduce actions. So a Markov decision process is a Markov reward process with actions or decisions. So we just add another set there, script A, and now we make the transitions depend on the action, and also the rewards depend on actions. That's all. Okay. That's the only change from the previous 2 objects. And now, any questions? Okay. And now that we have introduced actions, we can again discuss policies. So the moment we introduce actions, we can discuss policies, and the policies are just as we had described a few slides ago. Policies are just going to be mappings from states to actions, or for every state there could be a conditional distribution saying with which probability you're gonna try, it wants to try a particular action. Okay. So it's just at every state, what is the probability with which I'm going to pick some action. If it's a stochastic policy, if it's a deterministic policy, for every state it'll just say what action I want to take next. Okay. Any question? Okay. So because we went from Markov chains to Markov reward process to Markov decision processes, you can see that given a Markov decision process and a policy, the state sequence is a Markov chain, right? Given a policy, we have kind of suppressed the A term. So in the sense, so given a policy, there's going to be a reduction in that transition probability function. So which will ensure that this sequence of states is just a Markov chain. Okay. and also the state and reward sequences are just a Markov reward process. So fixing a policy, it just becomes a Markov chain or a Markov reward process. If you ignore the rewards, it's just a Markov chain. Okay, where this p superscript pi is just is a function of the full description of the Markov decision process parameter. Because you fixed the transition pi, you fixed the ways in which you can go to the next stage using the policy pi. That's why there's no more a in the description of the transition kernel or transition function for the Markov chain or the Markov reward process. Okay. So it's just we went from Markov chains to Markov reward process to Markov decision process, and I just said if you restrict to a policy, it just becomes a Markov reward process or a Markov chain. You just look at it either way. Now, for Markov decision process, we can also talk about value functions. Just like we said, there's a value function associated with the Markov reward process, and it's just going to be the same thing. For a given pi, we just said it's a Markov reward process as well. So for a given pi, you just collect all the rewards that are going forward. Okay. There is no action involved because pi is completely specifying the action, and it's completely specifying an action given a state. So it's like, because I know this is my starting state, I know what action I'm going to take next, and since I know what action I'm going to take next, I know with some probability which next state I'm going to land next, and st+1, let's say. From st+1, I know because of my policy which action I'm going to take next. So the actions are not there here. Okay. Very related value function that will be useful that was useful in the last lecture was the notion of action value function. So action value function is the expected return starting from a state S, just like here, but you take an arbitrary action A and then follow the policy pi. So you're just delaying from what point you want to start applying policy pi, start using policy pi. Okay, you kind of getting back 1 degree of freedom back to you, in the sense you can exogenously tell which action you want to take, and then you're going to land in some state st+1. From there on, you're just going to apply this policy pi. Okay. So that's the action value function or the state action value function. Okay. And just like the recursions that we saw in the Markov reward process, which was this recursion that we saw in the Markov reward process, for a fixed policy pi, the action value function is also decomposed into other action value functions. So an action value function at a state S and action A can be expressed in terms of other value functions, which are potentially different states and different actions. Okay. So pictorially, this is what's happening. So let's denote the black dots by actions. Okay. We can denote the black dot by state, actions. So there was a previous state and an action taken. So let's denote that by the black dot, and the circles as usual by the states. Then this recursive equation from the previous slide, this expectation, this recursive equation. I've just removed the expectation, explicitly written down the expectation. It's the sum of the probabilities of transitioning to a state S prime times this term here. Okay, and so I've just expanded the expectation operation inside for this quantity here. Okay. This equation is what is represented in this diagram. So for a state action value pair, state action value function at some state action pair, it's going to be related to other pairs, a bunch of other pairs, which are these pairs, which you can reach from by one hop by one hop basically. So is the state action value function clear, or any questions? Yeah.
Can you go back to the previous slide?
Yeah.
Yeah. So here, so if you look at Q by, right?
Yeah.
Action value function.
Yeah.
So you're saying AT is equal to A. So given action A,
yeah,
you are going to be proceeding with some probability. Or
yeah.
The expectation is this.
Yeah. You're fixing the state S and an action A.
Yeah.
And then you know that because of the transition dynamics of your Markov decision process, you will go to some state st+1.
Okay.
Right.
So at some time t dash, let's
Yeah.
say the action that we are exogenously applying stops.
No, we stop it after the first round itself. Exogenous action is only one, right? That's why it's a function of the. This is going to be a function of only exogenous quantities, and the only exogenous quantities are which state you're going to start and which action you're going to apply at that state.
Okay.
Beyond that, it's all completely determined by the dynamics and the policy.
So does that decompose into the value function, state value function?
Yeah. So these two are related. Yes, the state value function is just the expectation of sum over.
All A's for the first.
Yes, it's basically phi of s is just the sum over actions of probability of taking that action times q of q pi of s comma a. This doesn't write.
Okay, so we take the action on the initial state itself. Further down the line, like at t plus 1, we do not change that action.
At t plus 1, your action is determined by the pi. So if you are at st plus 1, pi will tell you what action to take from that point onwards. So you take an action, so you are at state S, you take an action A, you go to st plus 1 actually. That's we're using. At state st, we said we're going to start at this state, we're going to take an action A. Through the transition dynamics of the system, which we will not know in the reinforcement problem, but we'll get to some state st plus 1. From here, the action is is fixed. It's pi of st plus 1, whatever that is. Since pi is predetermined, pi will tell me in the state what action to take. It could be probabilistic, it could be deterministic. If it's deterministic, it will tell me a single action A. If it's probabilistic, it's actually a distribution, which is like a coin flip, which will pick some action at some probability. And then you go to st plus 2. And again, from there, you will take an action according to the pi. So let's say it's a stochastic policy. It's pi of a given st plus. That would be the transitions. And the same recursion is just illustrated here explicitly. It's just saying that these two quantities for two different state action pairs are related. Okay, not just two. Here there is actually a summation over all the potential states that you can reach and all the actions that you can take from that state. Okay. Now we can define the objective of the Markov decision process. So since we can exogenously apply actions, we can optimize for something, right? And what is that we can optimize? Because there's a number being generated for being in every state, there's a reward number, and so we can maximize that reward. And so, which is essentially, and it's not just we want to maximize, instantaneous rewards. We can maximize the sum of those rewards, and that's precisely the value function. Okay, expected sum of the rewards. That's precisely the value function, right? So the value function is, remember, v pi of s was just the all the rewards that I was collecting starting from state s by applying my policy pi, right? So I can now talk about, okay, since I have to specify a pi, I have to tell you every state what action you want to do. Can you kind of maximize over all such prescriptions to figure out v star of s? And you can do this for every starting state s, okay? And the optimal action value function is also similarly defined. Okay, maximize over pi of this for every s comma a. Okay. So that's the objective. So objective is to now optimize for policies such that you can maximize the value function, or you can maximize the state action value function. State action value function. Okay. So it turns out that even so we are just calling, so let's say there is some pi which maximizes this. Okay, we are just calling that star. Okay, we could call it pi star, but here we are just denoting, we are removing the dependence, extra symbol pi. So even for this optimizing policy, you still have a recursion, just like the recursion that we saw a few slides ago. For every policy, we saw a recursion. Okay. So the recursion is going to be called, the recursion for the optimal policy is going to, or the optimal value function is going to be called the Bellman optimality equation. So here I'm showing the recursion for the optimal state action value function. Okay. So that recursion, this also follows the recursion. So the optimal state action value function at a given state and action is going to be related to a bunch of other state action value functions. Okay. These values at different states and actions. Okay. So similar recursion to what we saw before. The twist being now we have substituted stars. Okay. And also the twist being there's a max operation here. It's called the Bellman optimality equation. So previously there was no max operation here. Does it look intuitive or does it look suspicious?
Like what exactly we're doing with this?
So I just defined this recursion for let's say the state action value function for every policy pi, right? This was the recursion. It's just showing that this depends on, this can be computed. If I knew all these guys, I can compute this. That's what recursion is, right? Yeah, it's basically somewhat related to dynamic programming in the sense if you know outcomes at final stages, then you can recompute outcomes at some stage beforehand. It's like a stage-wise thing. So here, all I'm trying to say is there is no notion of which is before and which is after. I'm just saying that there's a bunch of other states and actions for which there is these numbers. I can use those numbers to determine what the number is at this current state and action. Okay. And the next part was just saying that the same recursion also holds when, not the same, but a slightly different recursion also holds when you have the state action value function which is optimal. Okay. Why is it a different recursion? Because of the optimality issue. Because of the optimality property, you need to use a max operation here. Okay. This is a property of Q star. That's it. So why are we talking about these recursions? Because this will help us try to actually motivate a little Q learning again. So last time we just saw Q learning as a black box algorithm where we just said, okay, you're in this state, compute a couple of numbers, update your Q values and proceed. That's what we did last time. So we're going to now again revisit Q learning, which is going to be, so once we define the objective of an MDP, okay, and we know that MDP can kind of model formally a reinforcement learning problem. Now we want to find the best policy for the reinforcement learning problem. In reinforcement learning, you don't have access to the transition dynamics or the reward functions themselves. You can only interact with the world and get an idea of what is the sequence of states that you can visit or get an idea of what rewards you're collecting. That's only through experience, through trial and error. So typically you need to do a couple of things. Ideally, to come up with a way to get to a best policy, you need to have a couple of handle on a couple of things. The first thing is prediction. So what you should be able to, at least your algorithm or whatever solution you want to come up with, should be able to evaluate a policy, right? So if I tell you, if I give you a policy pi, the algorithm should be able to at least say, okay, how good is this policy or how bad is this policy, right? And the second thing is algorithm, of course, has to make improvements. If it's an iterative algorithm, it has to make improvements on pi so that it can eventually get to pi star, which is optimal policy. We last time we picked up Q learning, and this time also we're gonna just look at Q learning. It does prediction and control simultaneously, although we will not explicitly talk about prediction and control operations in Q learning itself. This would be a template for a lot of other algorithms that you may or may not come across if you look at reinforcement learning literature. Okay. So how to motivate? So this is, I guess, an alternate motivation for Q learning, which we did not see last time, which was if we knew the model. Okay, let's say we are not in the reinforcement learning setting. Let's say we know the model in the sense we know the transitions and the reward functions. Then it turns out that the Bellman optimality equation, we can turn that Bellman optimality equation into an iterative update to get to Q star. This is called value iteration in the MDP literature. So So the same. So this is just the same equation of balloon optimality equation that I've reproduced here. So what is the algorithm to learn Q star? Okay, if you know this P function and this R function, then you just replace this equality sign with a right arrow. Okay, it just says that and maybe write superscripts which are, let's say, k. Okay, so Q star at k plus 1 is going to be a function of Q stars at kth iteration. So I'm just changing this equation to an iterative algorithm. And how I'm going to do that? Start with a bunch of numbers, a bunch of arbitrary numbers. For every state and action, let's say you keep an arbitrary number. Now you use those arbitrary numbers and the current rewards to update the next values of these same numbers, right? So, and then you just do it again and again and again, and you will see that this actually converges to numbers. It doesn't explode or behave in a bad way, and so those numbers will actually be Q stars. Okay, so that's the iterative algorithm if you know the model, and it's called value iteration. In this case, Q value iteration. There's also just the state value iteration algorithm, which is pretty much similar, except the update equation is slightly different. Okay. So let's say you don't know the model. So what is that you can do? You will have to do a couple of things. Since you don't know the model, as I said, but you have access to the world, in the sense you can do trial and error, you can experience the world, so you can just do sampling. So in the previously we used to have this summation because we know the dynamics of the world. So since we don't know the dynamics, if I'm in state S, just try to take an action and see what next state you will get to. So that's what sampling is. And also instead of and also I'm going to change this iterative update that I was talking about in the previous slide to an incremental iterative update. In the sense, I'm going to now I'm going to do a slightly slower update. So we'll see the update pretty soon. And also the second thing is we'll have to do some exploration, because let's say I start with some Q values and I do an iterative update. It may be that I will not touch some states and actions because of which those Q values will not move. So I'll have to do some exploration. Basically, this epsilon or epsilon greedy type of, with some epsilon probability, I need to take a random action. So that's something which is an important ingredient once you don't have a model. So there are two important ingredients. One is you can sample, that is you can experience the world, and the second thing is you can experience the world randomly at least some time. Okay. So how do you do that? So we're going to change these two. So let's start by changing. So the first change is going to be sampling. So let's say I'm in state S comma A. Okay. Then let's say I'm in state S and I'm taking an action A. Okay. Then I'll get an instantaneous reward R, and I'll reach to state S prime. So that the environment will give back to me, right? S prime. And let's say from S prime, I can take action A prime. Okay. So that's just represented by this one thread. So if you remember the previous slide, here we had many threads, right? Sampling is just saying you follow one thread. Essentially, that's what the next diagram is. And the iterative update I was talking about is this. So I changed the equality to a left arrow, and I'm doing incremental averaging. So if you look at this expression, it may look contrived, but it's just saying that the Q value at, let's say, kth iteration, although we're not talking about iteration, let's say the k plus 1 iteration of an algorithm would be equal to 1 minus alpha times the Q value at the kth iteration at a given state in action, right? Two numbers here, two fixed things here, plus alpha times a quantity which is going to be R plus, in this case, r plus gamma times qk at some other s prime comma a prime. Let's say this is s and a. Okay. This is the same expression as what's written over there. I mean, this right arrow just means equality because they didn't index the q's with superscripts of iteration index, so that's why they put in a left arrow. But otherwise, this is the equation. Can you compare this and see that they are equal? Okay, I've used capital letters and small letters here, but modulo that. Sampling just means just this, right? Instead of this tree, I just go down some path. And which path will I go down? Because the environment is random, if I take in state S some action A, I will randomly go to some other state S prime, right? That's S prime, and from that S prime, I can take another action A prime. So that's what one thread is, okay? And if I decide to take some action A prime, then these two will determine S prime comma A prime. So those two will determine a Q value, right? And I got an instantaneous reward R, so that those two are factored here. And I have a previous Q value from the previous iteration that is still there. So I'm doing an incremental averaging, right? So I observed something new. I had a previous value of Q. I'm just updating that to a new value of Q at a fixed state and action pair. Right? Any questions? So to understand this, as I said, before getting to the Q-learning algorithm, if you knew the model of the world, then this would be then this was the original Bellman optimality equation, but the Bellman expectation equations were the same thing except for there was no max here and there would be a pi there, right? Instead of stars, there would be pi's. So how would you convert that into an iterative algorithm? You would just say Q at s comma a for a given phi is just there's an equality there, but I can just at k plus 1 is equal to Q. Let me just write it. R plus sum over P S prime. Yeah, I guess that's a pi. So okay. Some more all next states. So here the recursive equation is just saying you had a bunch of Q values, okay? Just use them in this left hand side, substitute the Q values and update for every s comma a, you will get an update, right? I'm just saying that this is k plus 1 and this is k, and you can do this because you know this guy. If you know the model, you will know that guy, and so from the Bellman expectation equation, I can do this. Expectation equation has no case here, right? Otherwise, it's the same. What I've written here. Yeah. Now I've just introduced iteration indices, and I'm just saying that if you do from the Bellman expectation equation, you can define what is called the or actually now the Bellman expectation equation, you can define what is called the value iteration algorithm by just instead of making it a function of pi, you introduce a max operation here. So max over a, max of a prime, and there is no pi here. So this would be the iterative form for value iteration, Q value iteration. Okay. So from here, we just said since we don't have the model, which is basically this square box here and this guy here, we're going to get a sample, and the sample is going to be just the immediate reward in that experience and some next state that I went to, a single next state that I went to, and with that I can just do the same type of an update. Okay. Yeah. Now to get to Q learning, so this next state, from the next state, the action that we took, it was arbitrary. Okay. We can decide to take that action to be the action that maximizes the next state's Q value. So from the next state, I can take a bunch of actions. I'm going to take that action which maximizes its Q value and only substitute that in my update equation. And that actually just gives us the Q learning algorithm. Okay. So it's basically an intuition of how did we get to the Q learning algorithm. We started with this recursive equations for the value function. And then we said, okay, we don't have the model, let's make it a sample-based thing, and we just made it incremental because we don't want to forget the previous values of Q. So we are learning something, then we just want to additively modify it to get to some final value. So that's all. So that's the incremental part, and exploration is just, so when I do this update for a given state, I take an action. What is the next action that I need to take from the next state S prime? Although the update equation says, update equation is not telling you what action you're going to take. So the next action is going to be based on an exploration exploitation paradigm. So let's recollect what the Q learning algorithm was. So you initialize a Q table, which is going to be the number of states times number of actions. So think of it as a matrix with rows being states and columns being actions. And so each entry there is the Q value for that state, action pair. And for every time step, you take an action. With some probability, you just choose it randomly of the allowed actions in that state. And then with some other probability, you take the action that maximizes the Q values for that state. So this Q value is just an entry in the table, and those entries will get changed. But whatever the current entries are, just take the action with the highest value for that state. Okay. You take that action. Now, because you took that action, you went to some next state st plus 1. Okay. Now, and also you got a reward rt plus 1. So you got two outputs from the environment, st plus 1, rt plus 1. You can use those two, rt plus 1 and st plus 1. You're not using, and you will also use the action that you take and just do the Q value update, okay, for the current state and action that you took. That's it. So you're updating an entry in your Q table in this way. And this is called the temporal difference error, but it doesn't matter. So this is the Q learning update, and you just repeat it forever, and that will give you the optimal Q values. In a sense, it will give you Q star. Sorry, this should be small Q star, but it will give you Q star. And the nice thing is here you don't really know the dynamics of the environment, right? We are not in the MDP world. We are in the world of trying actions and getting some rewards and figuring out the Qs. So once you find the Q, then you know what the optimal policy should be. Why is that? Because Q state action value function says how valuable is it for me to be in a certain state and take a certain action. And then what is the optimal policy? Just take the action which is the maximum over all Q star of S comma A, right? There will be a Q star S comma A1, there will be a Q star S comma A2. Let's say there are only two actions. Then just pick the action which is the maximum among them. That is the one which is going to give you the most value in expectation. That's what you figured out, right? So that's the policy. So that's Q learning. Just a recap. So Bellman optimality equation gives rise to the Q value iteration algorithm, and you make this algorithm incremental, sample, and adding the epsilon greedy exploration. These three ingredients will get you the Q learning algorithm. And you can now, I mean, we have skipped the formal way of deriving it. We just intuitively said adding these three ingredients will get us the Q learning update from the Q value iteration update. Okay. Any questions so far? Okay, so that was for tabular queue, when you could say, think of queue values as numbers associated with each state and action. You can think of it as a matrix, right? But that's not the case. So think of an agent navigating in the real world, which is on the left side. Then your state is just going to be the position on the grid, right? It's just going to be an x comma y number. It says, okay, you have five cells on towards the right, and maybe one cell above. Okay, that's going to be the state, and your actions are going to be, let's say, forward, backward, left, right, and there's some reward and so on. So that would be a state for a small scale toy example. Okay, toy environment. But the real environment, not the real, but slightly complicated environment, would be your states are camera views in front of the robot or an agent, right? Then how many states would there be? I mean, if you think of just a vision sensor, a camera, then the moment the camera moves by, let's say, 1 degree, rotation, then you get a different image. So would you call that a different state or not? So the states are too many, and for this you can't really even tabulate your Q-learning. You can't even tabulate the data structure that you use for Q-learning, right? If it's just a matrix. So that's why we'll next talk about function approximation, and that's where CNNs will come. So any questions before that? Okay. So now we look at function approximation. So what we are essentially going to do, is we'll use a deep network or any other function class. What does a function class mean? It's just a family of functions parameterized by some parameter theta. Okay, so linear function class just means all linear functions which are possible, and they're all parameterized by those coefficients of the linear function, right? So that's what a function class means. So we'll use some function class to represent either the value function or the policy function or the model. Okay, and because we looked at Q-learning, we're going to try to approximate the Q value function. Once we can use a function to represent the Q, state action value function, then we can use, if it's a network, then we can optimize this network end to end, which just means that we can optimize the parameters of this function, this approximator, using, let's say, stochastic gradient descent, to ensure that that function approximator is close to the true Q stars, right? And we can do this optimization either incrementally or in batch mode. So what exactly do we mean here? So let's say we have these many numbers that we were initially storing, right? Number of states times the number of actions. For each state and action, we would have a number, right? A parameter. Instead of storing them in a table, we want to find a more scalable way to capture these Q values, and to do so, we want to add this additional parameter W. Okay, so Q SA comma W will approximate Q star of S comma A, which is a huge. So this is a function, right? This, for every state and action, it's giving us number, so it's a function. We're going to approximate this function with another guy. It's called a function approximator, which hopefully will have lesser degrees of freedom. So W can be maybe 10 dimensional. Okay, that means there are only 10 numbers. If I fix a W, then I'm just setting 10 numbers, and that will tell me all the 100 other or 1000 other numbers that populate the Q table, right? That's what a function approximator is going to do. So pictorially, it's just drawn this way. It's where there are two inputs, state and action, and there's an output Q of S comma A for a fixed tunable parameter W that we're going to tune using optimization. Or a slightly different view is the same thing, where you input a state and you get back the Q values for every action that are possible. It's just a representation. The reason why this representation is interesting is because it looks like a multi-class classifier. That's all, and we actually probably will use a multi-class classifier like that. Is actually used. So anyway, so what are these functions that I'm talking about? What are these approximators? So to approximate this gigantic table, we can use a linear function approximator, or a decision tree, or a neural network, or basis functions, or nearest neighbors. Anything parametric or non-parametric functions can be used to approximate your Q star function. Okay. So So this is what we're doing. So we want to get a W such that Q hat of, so this other function is close to Q of S comma A. So for let's say for a fixed pi, if you can approximate this, okay. To do so let's say we can do that for a fixed pi. So let's forget about the Q star function, which is the optimal action value function. Let's say for a fixed pi, there's a bunch of Q values that I can associate with every state in action. I want to approximate that with another function, which is parameterized by W. So what should I do? Any ideas? So when you want to do approximation, then if you have the targets, if you know the values of the if you know for every not for let's say if you know for every S comma A what is that number, then you know the domain, you know the range, right? So you can just use, let's say, least squares or something like that to approximate, okay, which is what we'll do. So we can just minimize the error between this, okay. We can, let's say, for every state in action we know what this number is, and for every state in action we know what this number is for any parameter W, and I'm just going to minimize the expected square distance, okay, between this, where expectation is taken over pi.
So if we use, let's say, a network here, is this the loss function?
Yeah. So this is the loss function. If you know the targets, like if you know this, then this is just it's like labels or in the dependent variable values or whatever. Yeah. So if you want to approximate this guy with some function, then you just optimize that function. So this is going to be the score or the loss for that parameter, right? Then you can just use once you have determined the objective and you want to kind of tweak the W's, then what do? You can use your favorite optimization algorithm. You can use stochastic gradient descent, for example, to get to some optimum, some good value of the parameter W, which such that this error is close. So this error is small. It just means that at that value of W, this guy is a good approximator for the original function, right? And you can do that for the squared loss, and for the squared loss, yeah. So for squared loss, you can see that the negative half of the gradient, the half is just to cancel out the 2 there, otherwise you would have a 2 factor there. So the negative half of this gradient is going to be equal to this term times the gradient of Q with respect to W, okay. This is just straightforward calculus. So because we know the gradient, I can update the weights or the parameter as so let's say delta W is actually equal to W, okay, W k plus 1 minus W k. W's are weights or parameters of your model, or weights or parameters of your approximator, right? So this is just a gradient update. I'm just saying that delta W is Wk plus 1 minus Wk, which is equal to, in this case, this is equal to alpha times the gradient of loss with respect to W, right? So this is what that expression is. Oh, actually, this should be me. So we go in the negative direction of the gradient, right? So if you remember from many classes ago, for example, for CNNs, you saw that Wk plus 1 is equal to Wk minus alpha times the gradient of loss with respect to W, right? This what was the gradient update. So the same thing, I'll just put this here and call this delta W, and minus alpha times the gradient is just written over there. The additional 1/2 factor, but you can just ignore that. It's just constant. So what is so let's look at one concrete function approximator, which is if you can encode your state comma actions using a feature vector. Okay, so now we are talking about not explicitly representing a state and an action. Okay, we are talking about a state and action, a feature that represents that state and action pair, and it's going to be n dimensional. Okay, for example, for example, for self-driving, it can be the state is the car is in the center of the road and the action is go straight, right? Is it in the center of? So it could be a first, for example, first coordinate of your feature vector can be an indicator variable saying is the car in the center of the road and your and your action is go forward. So that can be 0 or 1 depending on the actual car configuration, which is actually the state. Okay, so things like that. And the second coordinate can be how far is it from the left pavement, how far is it from the right pavement. It doesn't have to be functions of both states and actions all the time. It can be function of just a state, it can be function of just the action, or it can be function of both of them. Okay, so a feature vector which is n dimensional, and let's say we use a linear function class, which means that we're gonna have this approximator function be feature transpose some weights. Okay, that's what a linear function class is. Okay, and explicitly written out here elaborately, which is not necessary. And if you look at this linear function class, so what is the gradient of? Q hat with respect to W? So if you have, let's say, F is equal to X transpose W, then what is the gradient of F with respect to W? Yeah, I mean you can say X transpose or X. This is basically n dimensional, n cross 1, and this is n cross 1. This is what is the gradient. Okay, so W is n dimensional. Then you can just plug this gradient in here and do a gradient update. If this was the loss function you're optimizing for, but that's not the loss function, right? We just saw this least squares loss function in the previous slide, and that had this term gradient of your function with respect to W. So that's why we just computed that, and we just said that is equal to the features, and we just put the features there. Okay, that's your gradient update for a function approximation, and this is kind of independent of reinforcement learning. We're just saying, given a bunch of functions, given a desired function, if I want to approximate it with some other family of functions, this is what I need to do, right? Now, that is if we, so now, but the thing is, I've been putting this guy in a blue square. That's because we don't really actually have this value, right? We are in a reinforcement learning setting, and for that means that we don't know the Q pi a priori. We have to do trial and error or something. So we may have an estimate at any given point of time of this guy, but we don't know the correct value. Okay, so we're gonna change this. Okay, in the next couple of slides. So again, to motivate the same thing, let's recall the Q learning update. The Q learning update was this, right? The new value at a given point would be previous value plus alpha times a difference, which was just the running average, which was 1 minus alpha times Q, the previous value, plus alpha times a new value, right? If you kind of do this update over and over and over again, and eventually what will happen is Q values will converge, right? There's a Q star. We just said that it will converge to Q star. So let's say if I do this update over and over again and it converges to Q star, that means that this value and this value is the same, right? At some point, eventually, this term and this term is going to be the same. I've not represented the k plus 1 and k here, but if you did that, then the k plus 1th iteration and the kth iteration would be the same values, which means that this term is going to be 0. It's just a way of saying that at optimality, when you have actually reached Q star, there is no error, right? I mean, this is actually just the Bellman optimality equation, right? Q of ST, AT is just the expectation of the next reward plus gamma times max over the next state, right? This is the Bellman optimality equation. This also motivates us to minimize the error between these two guys. Okay. This motivates us to minimize the error between these two guys. And so, from the previous slide, we said we don't have this, and from this slide we are saying at optimality at least these two numbers should be the same. So let's use this as a target. Okay, we can use these guys as targets instead of the q pi of s comma a that we were seeing. Okay, so we're going to minimize the empirical error between this guy and this guy. But okay, so now I've introduced w's here because now we actually anyway are going to work with approximations. You can see that I only highlighted one w. That's because this was just a stand-in for the targets, and targets are not functions of w, right? Here, this is not a function of w, right? If you look at the least squares, yeah, this is not a function of w. Because I don't have a handle on this, I want to replace it with something else. Because of the way Q-learning update looks like, I'm just reasoning that why don't we just put this as the target there? But of course, we don't have this. The whole point is we are doing function approximation. So instead of this, we'll put the function approximator itself. Okay. So we're going to minimize the empirical error between these two, where only this term is going to be the function of w. Here we're just going to assume that there's not a function of w. Okay. I mean, we're just going to evaluate it, and there's going to be a number there. It's not going to be a function of w anymore. So that's it. That's going to be function approximation for at least Q-learning. If we could kind of update w, but Q-learning works incrementally, right? So it actually is take one step, do an update. Now, how do we take one step and do this update, right? Now, instead of doing this update, we want to say we get a next state and a next state and a reward, right? We're gonna change our current parameter w such that the error between these two is minimized. So it's like a incremental update to w such that the error between these two is minimized. Okay. That's incrementally doing it, and we'll see that we can do it in a batch way as well. So what I'm trying to say is, if you can just replace the q object there with a function approximator, which is parameterized by lower dimensional quantity w, which can be weights of a network or some other parameters like the coefficients of a linear function class. If you can do that, then you will potentially have some optimization problem to solve over w. Instead of updating entries of a table, now you have an optimization problem over w that you may have to solve iteratively or something like that, right? If you use a linear approximator, it's going to be a convex optimization problem, and if you don't use a linear approximator, then it's going to be a nonlinear problem. In fact, if you substitute a deep network, then it's going to be a nonlinear problem because it's a highly nonlinear network, right? Function approximation function. As I said, we can either optimize it incrementally or in batch. So we are now departing from the Q-learning template. Instead of that table update that we were doing at every step, we have to do some other update, right? And so that update is going to be updating the values of w, the approximator. So we can do that either incrementally or collect a bunch of experiences and do it in a batch way. Okay, and we'll answer how we'll do it in when we look at the DQ and RL agent. Now, if you naively just replace the Q table with a function approximator, you will actually see that optimization may not happen. Like you may diverge off from approximating the Q values true Q star. Okay, and this is because the data is not IID. Okay, first of all, we are in a setting where your actions influence the next states, and because of that, the state action pair, the feature that you see now and the feature that you see next state and next action pair, they are highly related to each other. So the data is not IID, and also the polysynthesis and values may be too sensitive to the action choice. So that is not an issue in the discrete Q. If you think of a table, there is no relation between the Q of S comma A and the neighboring Q of S comma A. But here, once you think of an approximation like a linear approximation, it's really like a very smoothly varying Q values across states. Okay, but that may cause an issue because the original Q table looked very jagged. Okay. So any questions about function approximation in general? Okay, so let's look at given that context, we have just we said we can do function approximation. Now we'll actually see how it's done in a couple of examples. First one is DQN, which is not really complicated at all. It's basically just Q-learning with function approximation, which the approximator being a CNN. So let's look at that, because we have already seen CNNs before, and Q-learning also we have seen before, so this should be straightforward. So let's see. So before that, so why deep reinforcement learning? Why call it deep? Because we all know from the first 6 lectures, there's been a tremendous success in deep learning, and we want to bring in the success of deep perception or deep prediction architectures to function approximation. So the perception problem is to know what is there in the world, right? That's what a image classifier or a text classifier will tell. So what is it that's happening in the world, right? So that's the perception problem. So because of that success, we want to use them also as function approximators to represent features of our state and to represent our value function or policy function and so on. Okay, but you can't just use straightforward function approximation directly, as we saw before. It may lead to oscillations, divergence, and so on because of non-idealness of data and so on. We're going to now look at what were the few additional tricks that these guys employed so as to make that function approximator, which could be a deep network, work for playing Atari games, or playing Go, or even self-driving. So why deep representations? I think I've talked about ImageNet several times in the past. So the earlier architecture used to be like this, where you handcraft images, and now you actually have a deep network where you're directly feeding in raw image pixels, okay, and doing very little hand engineering. And specifically, especially with domains where you want to build an agent which has a camera as a sensor or some sort of visual feedback, or visual notion of a state, then a CNN is a good fit as a function approximator. And if you recall, it captures properties like local connections with weight sharing or pooling, right? So the same filter was being used in different regions of the image, or whatever is the intermediate tensor. So a CNN can be used as function approximator. So that means that the state is going to be this image, right? And maybe an action. So that action can be represented again as a numerical thing. So once you have this as the input, the CNN can be used as a function approximator in the sense that it can tell you what is the probability of it kind of approximates the value function for every action that you can possibly take from the state. Okay. So I'm thinking of the architecture where the state is going to be an image, and the output is going to be for every action a number. So that's like a multi-class prediction problem, right? So that's why a CNN can be a good function approximator. Okay. Of course, the objective is going to be the least square error rather than the cross entropy error. Okay, if you're going to train the weights of this function approximator. Okay, so let's look at DQN. So this is just a snapshot of all. This is about 50 games in the Atari learning environment. So what exactly is happening in the Atari learning environment? So basically, you're assuming, the agent is assuming that the rules of the game are unknown. Okay, you don't know. So the agent doesn't know what happens if they press the joystick left or right, or press fire, or any of those actions that are available. And the agent needs to learn directly from the interactive gameplay about how to play the game really well. And what is that instantaneous feedback that it gets? It's going to be the scores which are seen as pixels. Basically, the scores which appear at the top of this top of the screen. Okay. So this is still the RL environment, right? So you have in this case a state and a reward, and you get to enact actions. So that has a feedback loop. Okay. So what does DQN do? DQN just does Q-learning with function approximation. That's it. So Q-learning that you saw several slides ago and function approximation that we're going to see, which we saw briefly earlier, and we'll again retouch it. And specifically, it's going to use the CNN as the approximator, and there are a couple of extensions that it does to ensure that the function approximation doesn't diverge. So the non-IIDness of the data or the sequence of states that it's seeing, it somehow tries to kind of address that issue, so as to converge to a good approximation and converge to a good policy. Okay, and in fact, it converges to really good policies for many games. So, what is the function approximator? So, the approximator is, as I said, is a CNN. So, it's learning the value of q's, okay, q values from pixels s. So, s is going to be pixels. So, in this case, it's a stack of frames. Frames just mean those snapshots of the game, okay, which are coming at a certain rate as input. So, you just stack, and those are 84 cross 84 two-dimensional. I guess 84 cross 84 dimensional snapshots, frames, okay, and there are 4 such frames. So basically 4 such snapshots, okay. They can be color, black and white, or whatever. That will be captured elsewhere. I think it's going to be black and white. So here it's going to be 84 cross 84 screenshots of the game, and 4 such frames in sequence. So a snapshot now, what happened in the previous snapshot, 2 previous snapshots, 3 previous snapshots. That's going to be the S. And given that, I just want to predict what is the value of this S. Okay, I'm just calling that as the state essentially. Okay, or the observation. And the output is going to be 18 dimensions. So the classifier, if you think of a CNN's output, the number of scores it needs to have is 18, and that's it. So in this case, they have these many 8 cross 8 filters, which are 16 in number, and these many filters, and then they get into fully connected layers. So this is the CNN that is used for DQN. Okay, is the CNN function approximator clear? Which family or which function class that we chose is clear. All we now need to tune is the parameters of the filters, right? And the fully connected layers will have a lot of parameters, but we need to tune them. So that is all captured in that W, right? Okay, so once we have decided the function class that we want to use, then the question is, how do we update the weights, right? So updating the weights, I said we can use stochastic gradient descent, but the way reinforcement learning, the Q-learning algorithm works is it is at a given state and wants to take a given action, okay, and gets to next state and the next, it is at a given state, right? ST, and I take an action AT, and I get to ST plus 1, and I also see a reward RT plus 1. So this was what I did because of some reason, maybe because of the previous Q values. I took a argmax over all actions that was possible over here, and I took an action, and I got this next state and next reward, with which I was in the tabular case I was just updating the number, right? I was just updating Q of ST comma AT. This is what I was updating, right? Now, for function approximation case, I need to update the weights of this whole network, okay? Which means that for one new observation, I can potentially change the weights, right? That's what would be incremental. But an alternate variation is where you get the sequence, okay, where you are in a certain state, you took a certain action because of your Q values, or you remember the Q-learning algorithm. There was with epsilon probability take a random action, with 1 minus epsilon take whatever were the previous Q values, take the argmax at that state and take that action, right? You store this, you remember this for a bunch of iterations. So let's say for t is equal to 1 to 1000. Okay, I remember 1000 such tuples, okay, which are size 4 in number, which is basically state, action, next state, reward. These are 4 tuples. I remember them for some amount of time. Then this looks like a training data set, right? Now I have a sequence of such 4 tuples, and I know that this this and this and this kind of determine the target of my Q-learning update, right? The R, where was it? So this determines the R plus gamma max over, okay, AT is not needed, max of Q of ST plus 1 comma A. That would be the target. So basically with ST plus 1 and RT plus 1, I can compute this, and I'm gonna at some, with my function approximator, and then I want to so this will be the targets or the labels or whatever dependent variables, and the independent variables will be Q of ST comma AT. So if I collect this 1,000 of these, I can just do empirical minimization. I can just do a square and sum over 1 to 1,000. So I can have some expression like this where I optimize for the W. This is what you can do a gradient descent for this objective, right? We can change this W. Let's fix this W. Let's call this W fixed, because the target should not be also a function of W. So that's what. So this is what you can do to actually update the weights. If you take a gradient step, that's what you can do. So this would be called a batch version of the update equation. So in the tabular Q-learning, there was an immediate update. You can remember past and do a batch update as well, like this. Okay, and that's what is called experience replay. And since this part is not, I don't want to optimize the W in this, we fix the W, and that's just called fixed Q targets. Okay, so again we'll just repeat what's happening. So let's say we take an action AT according to epsilon greedy policy. In the sense we had a current approximate Q, right? At some previous with the current weights that I have a Q value. With that, I can take an epsilon greedy policy. It just means that take the argmax of the action, take the action which maximizes, which is the maximum at this state, with probability at state ST with probability 1 minus epsilon, and with epsilon take arbitrary action. Then what you do is you store that four numbers that are related to this step in a replay memory D. It's just a memory. It's just saying I want to store all the experiences. So in this step, let me just store this guy in my memory. Okay, and then what I'm going to do, what these guys do, is they sample a mini batch of transitions from the memory D. Let's say the batch is 1,000. So they just sample all these 4 tuples from memory. Compute the Q-learning targets. This is what these are the targets. Okay, with respect to all fixed parameters W bar. So you just compute this using your previous values. Okay, and then you just optimize the error between the network that you have, or the function approximator that you have, and the targets. These are numbers. This is a function of W. So you kind of do a gradient update, so such that the W's are tuned such that this error is smaller. Okay, that's what's written here. So they've written it in the expectation form. I've just written it in the empirical averaging form. That's all. And any questions about what's happening in terms of experience replay or fixed Q target? So those are new things which we did not see when we discussed just function approximation, right? So those are the 2 additional aspects to the DQN agent when it was trying to learn Atari. Okay. So okay, let's quickly. I'll just show you one more slide and then we'll break. So the same. So here I'm just representing the DQN agent in a block diagram. So what is the environment? The environment is in the blue color here. So the interaction with sun and everything else is going to be your agent. Okay. The additional thing that the agent now has is a replay memory, or a memory where it can store state, actions, next state, rewards. Basically, those 4 tuples, many of them. So that's the store procedure. So that's happening here. With the queue network, the agent can interact with the environment, right? Given the queue network, it can take these epsilon greedy actions. So that's what this is. Either it can take an argmax of the current queue network, or it can take an arbitrary action. Okay, and if it takes an action, it gets to the next state. The queue network itself is not going to use the reward, in the sense the reward is being stored in the memory. Okay, and now let's focus on this part. This queue network is going to get updated. How is that going to get updated? From the replay memory, you're going to sample many 4 tuples. Okay, that's state, action, next state, and reward. You will use the next state and the reward to get the targets. Okay, st plus 1 and rt plus 1 are used to compute numbers in this way. You compute those numbers. That's what's written here, max so r plus max of this, which is this. From this side, you just have the queue network, which is a function of parameter. Here just written as theta, but it's w. You can just minimize the loss between the targets and the function approximator, and take the gradient update and update the parameters of the network. Okay, so that's what's happening pictorially in the DQN algorithm. Just performance slide. The DQN agent does not know the rules of the game a priori. Any of the 49 or 50 games that they played, it doesn't know the rules of the game at all. It's just seeing the screens. It's getting the feedback signal, which is a change in the scores at the top of the screen. Okay, and there is no feature engineering of the screen. So screen, as I said, is just the 4 snapshots. Okay, because you can get to see the screen at certain refresh rates. So those 4 snapshots, and actually, yeah, it doesn't. Yeah, they take the screen inputs to be at the same rate as what humans can see. Okay, so otherwise there is some timing issue. Okay, so and there's also no feature engineering or hyperparameter tuning for the network parameters, hyperparameters, and so on. Okay, and the same network is used, same architecture used for all the games. And this plot is just showing on the x-axis all the games that they played, and y-axis is just showing percentage improvement. Okay. Yeah. The gray is showing what you could do with a linear function approximator, and the blue is showing what you could do with the DQN with the CNN as a function approximator. Okay, and these games are ordered in a way such that there is this line where below this the agent is performing worse than human, a particular professional human player, and to the left of this line, the agent is performing better than the human. Okay, so you can see that for some games it can perform way better than humans, and for some games it performs really worse. For example, it hasn't collected any reward. Or yeah. Yeah, these are normalized because the scores are all going to be different for different games, right? So that's the performance of DQN. So we'll break now and we'll get back in 5 minutes.
This is the challenge. We have to figure out this. Zeros has to take things better.
Next challenge is you have to
No. This is a puzzle.
Yes, this is different because Python has a lot of replace each character with provide an application. So it is called
Mapping is like every subject is this.
but Python is easy because it's interpreted. You can just like type those
Okay, so let's resume. So here's a small table which kind of captures why there are extensions about fixing the Q values of the targets, as well as using replay memory helped. So when there was no replay, and they were just using Q learning with incremental update of the weights, okay, then these were the scores attained in these 5 games, okay, and when they added fixed Q, okay, so this is the first modification when they froze the values of the Qs for some number of rounds actually, then they got an improvement over the scores, and then they added replay memory. They just added replay memory but didn't fix the Q values of the targets. So actually, in the previous couple of slides, I said fixing the Q values. That anyway you will have to do because you're substituting the update equation. So this anyway you were doing before, right? So when we say fixed Q values here, we are going to fix it for several rounds. So this is different from just saying that this is going to evaluate to a number. Yes, it is going to evaluate to a number because this is not going to be a function of W. But it's not just that. The extension that they did is that they kept this evaluation to be from a fixed value of W for several steps. Okay. So it's like using very old or stale values of W even when you are getting more and more experience. Okay. And that kind of helped them, as you can see in the slides. So when they just did Q learning, when they just did Q learning with fixed Q, they got improvement over not having. This is the vanilla Q learning, okay. And then when they added the fixed Q version, they got an improvement. When they added for Q learning, they added replay, they got some more improvement. When they added both, they got several orders of magnitude improvement. Okay. And after that, I think a couple of years ago, there was an architecture by Google which was doing the same thing, but in a very parallel and distributed manner. So the same actor is now many actors, many environments and many actors. Actors, okay. Actors just means the that part of the agent which is actually interacting with the environment. There's a learner, which just means that they are the ones focusing on the optimization of the W, okay. And there's a common parameter server, which just means that if there are many learners and many actors, they all have to synchronize in terms of the weights, right? So that's why there's a common parameter server. And yeah, in this case, 100 actors, 100 learners, and 31 parameter server machines. And so in terms of actually getting the experience, you can see that they reduce the computation from 14 days to 6 hours per game. Okay, and this is the 30x speed up using quite a bit x compute power. So they really had to crank up the compute power to decrease the time. I mean, basically by parallelizing, they were able to decrease the time to train a really good agent, right? So that's actually a general caveat that in general RL will require experiencing the environment many times, and especially if it's a complicated environment, you need billions and billions of experiences, and that's because of the trial and error based approach. And it's not clear how to improve it without adding extremely high amount of domain knowledge. Okay, if you of course introduce a lot of domain knowledge, you can reduce the time needed to learn a good policy. So it may be impractical for many complex tasks unless you do it in a careful way, and that's why there have been a couple of there have been successes, but not too many successes as one would expect. So that's the caveat. So let's go to the second architecture. So any questions about DQN? Yeah.
So once it learns, how does it retain, and after everything it learns, then is it like the...
So the information is retained in the Q network, right? So the function approximator knows what to do. If you know the value of being in a state, and taking an action, that's it. You just need to know that to kind of perform optimally in the environment, right? In terms of expected reward collected.
So the replay memory can be fetched so the Q network.
Yeah, at the end of training, you don't care about this. You just care about the Q network, which is interacting with the environment. The weights of the network, like even in vanilla Q learning, it's just the entries of the table that are relevant. Once you learn the entries of the table, you don't care about all this.
It's not required. Just like how the training data is not required, so it doesn't need.
Whatever you have seen in the past. In fact, if you saw the Q learning, it was not even remembering whatever it did in the past. Everything was captured in the summary statistic, which was the Q values, right? Here, they're just retaining some past and subsampling from the past so as to break the IID-ness of the data. Okay. I forgot to mention that earlier, I guess. So this is to break the IID-ness of the data. Okay. So now let's look at AlphaGo, which is a game playing RL based agent. Okay. So what is Go? Go is a board game. It has about those many number of states. States are just configurations of the board. Okay. So because these many number of states, it's very difficult for computers to evaluate who is winning. So in a given board position, it's not, even a computer cannot tell you who's going to win the game. Okay. So what does the game require? It's basically there are two players and each player places a pawn on this board. So I think this is a 9x9 board. So there are 9 lines, right? So the professional board is 19x19, but basically just plays. So the white player and the black player plays pawns on the board in a successive fashion. And the game is that if the white player completely surrounds black player's pawns, then those pawns are removed from the board. Okay, and the game terminates when one of the players has conquered the most territory on the board. Okay, so in this case, you can see that probably white has more territory than black. Okay, so that's it. That's the game of Go. It was one of the only classic board games. Of course, it needs a qualifier, but it's one of the classic board games before 2016, where AI agents were not the best. Okay, so AI agents were not able to compete with humans. That's what it basically means. For all the other games, you have AI agents which perform really good. In fact, so here we have just listed the RL agents which can perform really well. So for example, for chess, you may remember, I think it's called Deep Blue. Deep Blue is an agent which can be superhuman. So RL based agent is not superhuman, it's international master level. So for Go, it happens that people were not able to crack the game, as in compete with humans till 2016. They have been able to compete, but not at the most highest level. So we'll see how AlphaGo kind of addresses that and kind of closes this issue here. So for that, we'll have to kind of discuss a slightly related problem to reinforcement learning. In fact, it's related in the sense it's a subset, which is called the forward search problem. So remember, there are two sequential decision-making problems that I had introduced a couple of lectures ago, but let's just recall that. One is reinforcement learning. When I don't know the dynamics of the world, I do trial and error, figure out the optimal policy. There was the other version where you just plan. Planning just means you know the model. Like, for example, in the MDP, if I knew the model, I would just do Q-value iteration, for example, to figure out the policy, right? So that's called planning. Okay. So planning is the other problem. The forward search problem is actually a planning problem where you know the model of the world and you can't compute pi, as in you cannot plan everything beforehand. So pi tells you in every state what you need to do, right? Pi is a policy which will tell you if given an MDP, if you do Q-value iteration or some variant, some solve, some algorithm, then that will tell you in every state what to do, right? But let's say the state space is so large that even if you know the model of the world, that you cannot explicitly quantify for every state what you need to do, okay? Then you just focus on what action you need to take next. In the sense, you just focus on what is the best thing I should do at this point of time, in the sense in the current state only. So you're not computing pi, you're just computing A star, which is the best action that you can take at the current state S or S star or whatever. Okay. So for Go, it just basically is how good is a position S. A position just means the configuration of the board, a bunch of white pawns and a bunch of black pawns. And the reward function is going to be 0 for whenever you're not terminated, and 1, let's say if black wins. Okay, it's a zero-sum game, so if black loses, white wins, and so on. So this is a reward. and now policy is going to be the moves for both players, because there are two players involved. Black makes a move and then white makes a move, right? So there are two players involved. So we're gonna just club both their policies and call pi the policy of the problem of this game. Okay, and the value function, which is how good is a position S, is going to be the expectation by following a certain policy for both the players of reaching a reward which is 1, right? Which is just basically the probability of black wins given starting state S, and following policies pi B for the black player and pi W for the white player, right? Pretty straightforward. And then we're going to define the value function, the optimal value function, to be maximum version like this, where the black player is trying to maximize the value, whereas white player is trying to minimize the value, right? Because they're playing against each other. So we're going to define the value function this way. Yeah. So let's get back to the forward search problem. So what is the we just define what the forward search problem is. Find the best action for the given state S. Don't tell me the whole policy. Now we can figure out forward. We can try to attempt to solve the forward search problem in the following way. So we basically want to select the best action by looking ahead, right? So here we're assuming that we have the model of the environment. Okay, it's just that the model is too complicated or too many states and so on, so we can't really compute pi. So what you do is you build a search tree. So a search tree is nothing but you start at the current state as root, and a search tree is just, if I take action A1, then where will I end up? Maybe I'll end up in these locations. If I take action A2, I end up in these locations, and just expand the tree. Okay, you can just keep expanding till the time you terminate, in the sense somebody wins or loses or something like that, right? So that's the search tree. For this, you don't need to solve the whole MDB, right? So for this state, if you just roll out the dynamics of the model or the world and get to some terminal states, and eventually you'll get to all terminal states, then maybe you can kind of figure out what action to take at this state. Okay, that's the forward search problem. And one way to kind of solve this problem is to simulate. Okay, so you have the model, you can kind of draw samples from the model. Okay, which just means that if I'm state in ST, then I'll take some action AT, I'll read some other state ST, which is by sampling from by interacting with the model of the environment, I'll read some other state ST plus 1, I'll take another action, I'll read some other state, same other action, and so on, it'll terminate. Okay, using such simulated episodes, I can kind of figure out what is the quality of taking an action at my current position. Okay, and for that I can apply Q-learning or things which were not capturing the model of the environment explicitly. I can use that. So any questions about using simulations for forward search? Yeah.
How is it different with here you said it's only should be at current state?
Yeah. Yeah, it's only at current state.
I mean, again we are going to recursion, we are going to all states, right?
All states possible from that current state. Yeah. Yeah, I mean, ideally you want, it could be that if it's a very cyclic thing, then you would maybe visit everything else. But especially in games, you will be progressing towards the end, right? So you may not visit some other states and so on. But it could be, it's true that if you visit all the states in your state space, then it maybe boils down to the original problem. Yeah. Yeah.
So at every subtree, does it try to take the option where, so that it has two branches, right?
Yeah.
So does it take the branch where the probability where there are more terminal states?
No, we'll now come up with an algorithm to do that, and then we'll use that in AlphaGo. So we just said, you can think of just branching out everything and getting an idea of what to do at this state, right? Which action to take. I can't branch out everything, so let me think of rolling down, some few of these paths from this state to the terminal, and then get some idea of how good this action is or that action is. But we'll see how to do that concretely. Okay.
Professor?
Yeah.
But this is assuming that the same state will not be referred again. Otherwise, it will be again. There will be no
No.
termination. It will go in loop, right?
Uh,
If same state, like
Yeah.
I come to state as t plus 1 and
Yeah.
then there's another option to go to state t, it will go in a cycle. So it will never be terminated.
yeah. So is it? I mean, so we are in the context of games. Is it possible to get back to the
You
same
can't.
configuration?
Once you put a stone on the table, you can't take it off. So
Okay.
it's not possible to work.
I mean, so that should not be an issue. I mean, you can bring in discounting and so on to get values. I mean, it's not like you have to go till the termination. You go to some point. So in games, you have to terminate because that's the only place where you see the reward. But if you have general MDPs, then there are different settings, and so something else will apply. So what exactly is the idea? You just simulate a bunch of experiences from the state. Okay, from this state, I just get a bunch of actions, rewards, next states, a bunch of actions, rewards, next states, maybe key of them, and then basically we can just use this experience to get an idea of what action to take at that state. Okay, and we are using model free because we have not seen model based reinforcement learning. So Q learning is actually a model free reinforcement learning. So we'll see. Anyway, we'll get to that. So we'll look at two variants of how to take a decision at this current state. One variant is the simple Monte Carlo search, which is actually just intuitive, and we just discussed it. We'll rediscuss it. And then what is called Monte Carlo tree search. Okay, that's the more interesting algorithm. So what is simple Monte Carlo search? It's going to be I am at a state ST. Okay, this small state ST, and I want to know what is the quality of taking an action A from that state. Okay, now I have access to a model from which I can generate these sequence of state action rewards and so on. I also have access to a simulation policy. Okay, so this is going to be somebody tells me some policy that you can follow for every state. Okay, but it may not be a good policy. It may be a good policy, whatever. Some policy is given to us. So given that policy, we can just so you can think of this as even a random policy, right? I can do a random choice of actions for next states and so on. So I've been given a policy, I've been given a model. I just get these numbers and take the empirical average. Okay, I terminate in some state, and at the state, since I only get rewarded that terminal state, I can just sum up out of k how many of them did I get a 1, for example, in a game, right? So that will tell me the quality of taking that action at that state. That's as intuitive, as it gets. And then you just pick an action which is maximizing the values of these Qs. Okay. In fact, Q is that, right? It's an empirical average of. Q is the expected reward that you can get by taking an action A and following a policy pi, which here we're calling it a simulation policy. Okay, we're just not indexing like pi subscript, but that's fine. So that's simple Monte Carlo search. With this you can actually play games. So as in play game players, build game players. So this is how it look like. You are in some position S, and maybe you played a action. You played an action. So that's already captured here. Let's say from that, let's say the next player plays something. You play something. Next player plays something. You play according to your simulation policy. You get to some position. Maybe you had you had more territory or you had less territory. You look at the outcomes, just take an average, and that's the value of taking that some action that you took here. Okay, is that clear?
Yeah, I mean it's almost coming to like probability itself, right?
How is the probability?
Because again the number of things are more. It's not like
Yeah, there are many. Yeah, you have to. Yeah, it's coming down to you are sampling from the model. Yeah, because otherwise there will be too many branches, right? So you can't explore everything to figure out what is the best thing you can do.
So again, something like cloning, which is obvious and not.
No, from the model you just sample, right? So that's what. So you have an access to a model, and you have simulation policy. For example, your simulation policy can be random, in which case it's already introducing randomness into the how you're going to touch the different states, right?
So there is some strategy involved in that simulation policy.
Yeah, somebody exogenously gives you here, at least in this one, and you're hoping that that policy is good enough such that you actually do well in terms of getting a good numbers, good value function such that you take a good action here. Yeah. So Monte Carlo tree search is a variation of that, where you've only been given a model and you're going to improve the simulation policy. Okay, so in the previous Monte Carlo search, you've been given a simulation policy, you're not touching that, you're just computing Q values and you're done. Okay, but now we're going to improve the policy itself. So the policy is going to change from one simulation run to another simulation run. A simulation run is just going to the end of the game. Okay, I went to the end of the game, got some value. In the next run, I'm going to change my policy, by which I'm going to go to the end of the to the terminal state or whatever, game end state. Okay, so how is it going to work? So Monte Carlo tree search has actually 4 steps, but we're going to focus on one step, evaluation step, and then just kind of ignore the other 3 steps in the sense of we'll just club them together to understand the algorithm. So because this is one of the key steps. So this is called the evaluation step, which is going to be you simulate k episodes from the current state using current policy, just as before. Okay. So you get this from a current policy and the model, you get these sequences. Okay, and then you compute for every state and action, you compute basically the value that state got. So from, let's say you are in some state S and you took an action A and then you went to the end of the game, then you got a reward of plus or 0 or 1, then you just attribute it back. Same thing that we were doing for Monte Carlo search, except that you can do this for multiple states, in the sense that I removed the dependence on t here. If you see, I said, okay, if you encountered some other state, okay, so this is also a state that I saw, right? I can also give a number to, so now I'm giving q, these value functions to other states and actions as well. So in my search tree, right? Previously I was just giving a q s comma a for only the actions that I take from the root, but here I'm going to give numbers to other nodes in the search tree. Okay. And the numbers, the way I'm going to give the numbers is the same as before. Just for if I'm at a node and I went to the end, so let's say I was in some node. I came to this node, this s comma a pair somehow, and maybe I went to the terminal state. Maybe I went to some other state and maybe came here and again I went to some terminal state. Then all those numbers are going to influence my q value here. And similarly q value here and q value here. Q value here will be all the paths that I took to different potentially different paths, right? Sequences starting from ST. So this is going to be ST. Actually, yeah, A has to be represented as well, but yeah. So now let's focus on how the policy gets improved. The policy is going to be improved as follows. Is simulation. So now I'm going to describe how the simulation happens. I just said we're just going to use the policy to get the simulation. So now we're going to describe a little bit about how the simulation actually happens, so that now we can say how the policy gets improved. And it's going to be as follows. In the simulation, there will be 2 phases. In tree and out of the tree. So what does it mean? So I'm at ST and I can take an action A1, let's say, or A2. Okay. At the beginning of time, I'll just have my what is this node? The root node as my in tree. Okay. Since none of the actions were tried, I can just try either action. I'll get to some state S1, let's say. I get to state S2 here, but let's say I tried this, I came to state S1, and from here I just follow something called the out of tree policy. Yeah, I call it default policy. So let's say there's a default policy. Okay, I follow the default policy here, and I reach some state, game state where I won. So I'm gonna give a q value to this guy, I want to give a Q value to this guy. I'm also going to give a Q value to this guy. If in the next simulation, maybe since I did not try this, I'll try this as well, and it goes through a bunch of states and it goes to 0, and I'll give a Q value to this guy. So this is what I would call the in-tree phase. So that's how I'll get a tree. And the border between the node here and the node here would be just that the next node has not been assigned a Q value yet. And then, so if this is a leaf node in the in-tree part, then from there onwards I'll just follow the default policy. Otherwise, if in some simulation I get to the leaf node, then I can expand and put another node into my in-tree, right? The way I did it for here, I started with this as my in-tree. I added these two guys into my in-tree part. Similarly, I can add additional nodes. So there's a slight distinction between the in-tree part and the out-of-tree part. And what is that? When I'm within the tree, I'm going to focus. I'm going to choose actions when I'm going through the paths based on the Q values. I'm going to choose actions based on greedily pick that action which maximizes my Q. So there will be a Q value related to st, a1. There's a Q value related to st, a2. I'm going to pick the one which is the highest when I'm in the inside. Okay, because I'm getting these Q values. When I'm on the outside, there's no Q values. So I'm going to just follow a default policy, okay, which is some hand engineered policy or a random policy or something like that, so that I get to an end state. Okay, that's it. So and why is the policy changing? Because every time I end my simulation, there's a number that I get 0 or 1 in a game case, and that gets propagated. So Q values get changed, right? So in the next simulation, because the Q values change, the policy is different, at least in the in-tree part, right? So that's all I mean by simulation policy getting changed.
Are we not going traversing till the end every time?
We are.
Where is the out-tree coming?
So actually we'll see in the next slide. So let's say we start from the current state. Okay, so there's some state start. Okay, some board position, and since at the beginning of time only this configuration of this state is in my in-tree part. So and I don't have anything anything to choose. So I'll just let's say I have two actions. I'll pick the first action. I'll try both actions now. I've remembered that I'll try both actions. I'll pick one action and I'll go all the way to the end. While going all the way to the end, I'll just use the default policy because there's nothing else I can do. Okay. So that's what I did. I went to the end, I got a 1. So I'm going to propagate it back and I'll tell the value of taking that action is going to be 1 out of 1. Out of one simulation, I got a 1 by taking that action, right? Is this clear? Okay. Then we'll go to the next step. Then again, let's say we, okay, when we did this, we're gonna, the next state that we visited, we're gonna put that in the in-tree part. Okay. That's going to be this guy. No, that's not going to be that guy. So the guy, the next state that we visited, that's this guy, is now going to be part of the in-tree because that node was the one which was the closest to the original in-tree set. Okay. Next, I'm going to try another action, and potentially I may go to another state. Okay. And again, let's say from that state, there is no, maybe that state is in the boundary of the in-tree. Then again, I'll just have to kind of do a random rollout. Use the default policy to go to the end of the network. Okay. And again, maybe here I see a 0, then I put it, go all the way back up. And when I'm backing up, all the nodes which are in the in-tree phase or in-tree set, they will have Q value. So here, since it was 0, 0 out of 1 is a Q value there. And since this guy tried 2 simulation runs, out of which in one run he got a 1 and the other run he got a 0, that's 1/2. Is that clear? Okay. So similarly, you can do that for another node. Okay, for the same thing. So maybe roll out maybe this time they chose the node in the first. Okay, I guess not the same. A different, an action such that they led to another action, as in a move such that they led to another board configuration, and again roll out according to the default policy, and that was 1,1 and 2,3 there. So you do these operations. When you did this, you're now gonna, as I said before, you're now gonna introduce the next board configuration as part of your entry. I didn't show that for the previous runs, but now you're gonna introduce. Okay, now we're gonna introduce next board configuration into your entry. Okay. Basically, here you're gonna choose directions based on the Q values. So here, for example, whether to choose this node or that node, you're going to choose this one because it has higher Q value. From here, maybe there were no nodes, so you just chose something at random. Maybe there were no nodes that were tried before, so you choose something at random and then you use default policy. So what I'm saying is that above this line, you're going to choose based on the Q values which are in these boxes. So 1/2, 0,1 and so on. And below that line, you're just going to play according to default policy. Like here, for example, you'll try another thread. So this part you're gonna, this was never tried, so you tried this and you got a 1,1. So the next time you may try, out of these two Q values, if at all you come this way, you're gonna, in fact you'll come this way, you're gonna try this one, okay? And you'll also add some element of exploration here. That's added by that's added by actually similar to something like what you see in multi-arm banners. So you can add a bonus function for how many times a node was visited and so on. Or you can just do random exploration. So somehow you need to introduce an exploration aspect here. But that's what Monte Carlo tree search is. It's all about the policy here kind of changes. Policy here is kind of fixed. And this part changes from one simulation to the next one because the Q values change. Okay. And the tree, so the things where you start placing Q values also potentially increase as you do more and more simulations. Okay, so what are the extensions for AlphaGo? Just like in the DQN, we said it was just vanilla Q learning with function approximation, which was a CNN, but we added experience replay, and we added those fixed Q targets, right, for several rounds. Similarly for AlphaGo, there are a couple of extensions, which is as so AlphaGo has to play a game, right? So which means at any given board position, it has to figure out what is the next action to take. So it actually has to solve the forward search problem, and it's going to solve the forward search problem using Monte Carlo tree search. Okay. The twist is going to be it's going to use a policy network and a value network to truncate the search tree, and I tell you what that is. But first, we have seen a value network, right? A value network just means that given a state, tell me how valuable being in this state is. What is a policy network? A policy network is going to be a policy function approximator, which just means that given this board position, what is the probability of taking a next action? Okay, it's like it's a network, but you can just think of it as a function which gives, given a state, tell me what the next action should be. It's a probabilistic policy, so that's why it's just telling me, okay, if this is a board state, probability of taking the next action, you should take, for this policy, the probability of taking next action, this one is this high, probability of taking next action with something else is this high, and so on. So it's just a representation of a policy. Okay, so there are two networks that we're going to use to kind of shrink that tree search, and we'll just see by pictures in the next few slides. So what is a value network? And it's just this, which is given a state. There will be a bunch of parameters, and it will tell me this value of being in a state, which is just a configuration of the board, right? And there will be actually a CNN. I think they use a CNN to kind of get to. They actually take a snapshot of the board to get to a value of that board. Okay. And what is a policy network? Policy network again is given the board. Tell me what is the probability of taking an action, which here I guess is placing a next what is that? Next pawn over here, over there, over there. It's a probabilistic policy. Okay, it's not a deterministic policy. And it's again a network given a state. A bunch of parameters will tell you what action to take given that state. Okay. So that search tree is going to look like this, right? In fact, for Go, I think this branching factor is like 100 plus, and yeah. So it is 100 plus, and then depth is also going to be enormous. Okay, it's like 100 to the power 100 or 200 to the power 200 or something like that. Okay, which is much more than a number of states. Anyway, we're not going to do that. So Monte Carlo tree search is somehow trying to do some, instead of doing that whole thing, it was just trying to sample a few paths and get an idea of which action is good, right? That was the whole point of sampling for forward search. Now, the AlphaGo's extension is to kind of get rid of certain part of the. Okay, can you actually see the? I can't see the tree, but oh yeah, you can see the whole search tree here, right? So AlphaGo's extension is to use a value network so that you don't keep going to the terminal state. Okay, at some point here you are in a certain state, right? S comma A. So it will tell you what the value is. Okay, so that's what we are plugging in to kind of prune the depth of that search tree. Okay, we are plugging in value networks there. If at all your Monte Carlo search gets to that point, you can just use a value network to tell you the value. Okay, and you'll also use a policy network to kind of guide your action selection. Okay, otherwise you will have to do the whole breadth, right? I mean, so there are so many actions so many places you can put the next pawn potentially. So the policy network will tell you, given a state, where should you most likely put the next pawn. So hopefully the policy network is is capturing a really good policy, so that you are actually exploring intelligently. You're not doing a breadth, randomly sampling an action and then going all over the search tree. You are actually doing a very focused next action, getting your next state, focused next action, getting the next state, and maybe at that state you don't want to keep applying the policy network again and again. You'll stop there and ask the value function network what the value of that state is and do backtrack. Okay, that's what AlphaGo does, and that's what even previous versions did, but these guys did it with CNNs or deeper networks. Previous versions did it with linear networks, and they reached decent accuracy, but not good enough to beat the best human player. Okay, that's the only difference. In the interest of time, we'll skip the. Okay, so we'll just describe how they got the networks, right? I mean, I said you'll use a value network, you'll use a policy network, but how did you get those networks? Okay, so this slide kind of captures how they got the network. So first thing is they had human experts kind of tell for every board position what's the best next move to make. Okay, and then they did the classification problem, solved the classification problem to train an initial policy network. So it just tells you, it's basically it's a classifier, right? It's just telling you, given the state, which of these hundreds of actions you can take. So that's the classifier, and the classifier is being trained by training data where humans have told, in this state do this, right? So it's basically emulating humans. After that, so that's the supervised learning. So that's what is the first part of the course was looking at. Second part of the course is, this part of the course, which is reinforcement learning, is about improving this initially trained network by playing against itself. Okay, so if you remember, the value function defined, at least for Go, was that there were two. The pi was actually two policies, right? The policy for the black player and the policy for the white player. So there are two policy networks playing against each other and improving themselves. Okay. They play against each other in the sense that you play something, you get to the terminal state, you see the value, you kind of update your weights. Okay, and this happens for both sides. Okay, and then so they got a good policy network, and that's it. So policy network, that's how they trained. Now, how did they get the value network? For value network, they just need value network is supposed to tell you in a given state a number, which is how good that board is to get to a terminal state. So what they saw is that for historically trained data, human trained data and so on, there's a very high correlation between one state and the next state, because clearly if board is in some configuration and you won, and there will be a slight change and you won, so they are very highly dependent data. So to kind of address that, they again made the well-trained policy network again self-play to generate few more board configurations such that there is a good mix of random board configurations, and they just trained. So this is again this is a regression problem, because the output is just a scalar, value of the board position, rather than what is the next action, which is a discrete finite number. So that's it. That's how they train these two networks. We'll skip the descriptions. We'll skip the descriptions. So that's how they kind of built this AI agent, which played the world #1 player back in 2016, and kind of won the games 4:1, I think. Yeah. Any questions about AlphaGo? At the high level, kind of you are able to capture how a function approximator is being used, right? Basically, function approximators are being used to prune the search tree. They are not solving the policy for the whole game. I mean, that would have been nice if it was a really small whole game, board game. You know what exactly you need to do for every position of the board. They are just solving. You are in a certain state. Tell me what is the best thing you can do, and that's the forward search problem. Monte Carlo tree search with net function approximators being used. Okay. So there are several topics that we did not cover because we covered reinforcement learning in 2 lectures, which is too fast. So like few things, for example, partial observability of the state. So in games, for example, you can probably get the full observability of the games of what is the exact situation. But in a more complicated tasks, you may not see. You will only make measurements through sensors, right? Through either cameras or position sensors and so on. So you'll never know the full state of the environment. You'll only know it through your measurements, and if some measurements you're not making, then you'll not know you'll not know the full state of the environment. Okay, so that is an important issue. We did not cover Monte Carlo methods in detail. Okay, Monte Carlo methods are, when you saw in the forward search problem, we were doing a simulation till the termination. Okay, in a game, but you can also do that for in MDPs, in reinforcement learning, till termination to get an idea of the GT. Because if you remember, GT was a return, and if you want to estimate the value of a state, you can, from a state, given a policy, you can just do a rollout, as in use the policy again and again, get to some terminal state, add up those rewards and get an idea of the value, right? You can do a Monte Carlo averaging. So we did not do that, and so there are many methods based on that. There's this whole area of temporal difference methods, which again we did not cover. So we saw temporal difference error definition in the Q-learning algorithm, but we did not really touch about what exactly these methods are, what exactly is the meaning behind the name, and so on. Q-learning is closely related to something called SARSA. Okay, SARSA just means state, action, reward, next state, next action. We did not look at policy function approximation. We just said policy function approximator was used in AlphaGo, but we did not spend time on how you can approximate a policy function itself. But it's very similar to what we did for value function. And we did not look at model-based methods. So Q-learning is a model-free method. Even SARSA is a model-free method, but there are model-based methods, which just means that through experience they reconstruct the model of the environment. They will reconstruct the transition probabilities and reconstruct the reward functions. And once they reconstruct that, they can do planning, as in solve the MDP using value iteration or some different class of algorithms. Okay. So finally, let's summarize. So R is a great framework to make agents intelligent. So you just specify goals and provide feedback. Traditional methods are not scalable, and that's why we looked at function approximation in this lecture to kind of get an idea about how to manage scale. It complements deep learning that solves the perception problem, as in what is there in the measurement problem. What is the state? Okay, is there an object in the state? That's the problem that deep learning is solving, and RL algorithms are trying to solve the planning problem. Planning problem when you don't know the model of the world. Okay, and DQN there were two additional tricks: experience replay and freezing Q targets over multiple rounds. In AlphaGo, the trick was multi-convex tree search with approximations, but the previous state of the art was linear approximations. They used deeper approximations using deep networks, so that got them to beat the human player, best human player. Many challenges still remain about exploration. We just said do an arbitrary action at random with some epsilon probability. That probably is not a good idea. So there are other issues. So that's it. So that's this. That's the self-driving car again from I think last lecture. There are videos of them actually driving in real streets, but this is one from CES, I think. Yeah. So any questions so far? Okay, so that's it for the class.
So one version of